when Lockheed, no, it was Martin, purchased RCA. It was, well, Martin bought it, but RCA is integrating them very nicely.
Well, that was embarrassing.
Why? What happened?
I went to Radnor.
Harold, you made it back.
I made it back. And I only killed 3 people on the Schuylkill
You
Expressway.
should have just streamed from Radnor, Harold. It's like
I did. I joined the meeting from Radnor, and I thought, well, I could sit there, but it's going to get cold. So,
Make me
well,
laugh.
it's funny too, because
They're cold.
I emailed Lou Berman earlier today, and I said, when I see you tonight, I'll give you something. And I also emailed Joe Lamb and said, I have an 8-inch telescope that's been donated to the club. I'll give it to you tonight, when I see you at the meeting. And nobody said, what are you talking about? Not one person questioned me.
I see
That's a
Joe
little
over there
sketchy.
giggling.
How's he going to get it to you on Zoom?
He's not getting it to me tonight.
Virtual.
I'm not getting it to him tonight. That's for sure. So, well, hello, everybody. Thanks for coming. We may as well get started since we're recording. I have a couple of announcements, and then I'll throw it to reports. The first thing is that we're going to reprise our Fort Washington adventure from last summer and do that again on August 19th. We will be back at Fort Washington under one of the pavilions to have a live meeting there. Our next formal meeting, Jeremy's got another meeting next week where we're having it's a sort of a 2-part presentation. Jeremy, I'll let you explain that. But our April meeting will be live back at Radnor, this time I'm sure. And we are making arrangements to be able to live stream our live meetings too, so that if you can't come to Radnor, you'll still be able to tune in. I saw George. I want to thank George and everybody else on the editorial board for the fabulous job they've done over the last several months. They terrific. Each newsletter outdoes the one before it. One other thing I'll mention, on July 27th, we have agreed to sort of supervise a star party for the Challenger program at Montgomery County Community College. The Challenger program is for kids. It's usually run out of Pottstown, but they're all going to come to the Montgomery County Community College campus in Bluebell because it's darker. And if anybody can help out with that, it would be great. Just shoot me an email. I'll also put the word out. We have lots of time between now and July, but I would like to get a bunch of people available for that. And with that, that's the end of my report. I'm going to throw it to Brian Lee for membership.
Excuse me, one question. What was that date in July?
July 27th. I made sure it was before Stellafane.
You said 2/7?
July 27th, correct. I think it's a Tuesday night.
It's a Wednesday.
Then it's a Wednesday, but it's before Stellafane. I made sure of that because I know there's a lot of members who like to go up there. Okay, Brian.
Okay, just 1 second. I'm co-host. I'm letting people in the meeting. So we have 6 new members this month. Garrett Wright, Anthony Rowan, which I did see in the Zoom tonight. So I'll welcome him right now. Joe Stoyak, Brian Kelly, Robert Dolson, and Eric Dolson. So welcome. Actually, I welcome to Anthony because I definitely saw him tonight. That's it for me.
Great. Thank you very much. Obviously, you're not going to have to collect badges tonight. And now, is Lou, are you here?
I
No, Lou's
don't,
not here tonight.
I have
he's
a lot
out
of
of town.
pictures. Okay, I have a lot of pictures on my screen, and I can't read quickly at the names. That's good. Then I'll skip that. Janet, do you have anything for outreach?
Well, we have the Anderson Star Party that was going to take place last week was postponed due to clouds, so that's now scheduled for the 11th of April. And I'd like to get everyone thinking about another event we have in July that we promised to do, and that's the Camp for Disadvantaged ninth graders that will be helping the Rotary Club with, and that's in Reading. I think it's the weekend of it's the 9th through the 11th or something like that. And I'll be getting more detailed information out into the newsletter on that. But basically the thought is that we will, the theme of the workshop, which is being run during the day, or the camp that's being run during the day, is travel to Mars. And they're using that as a jumping off point to talk about physics and biology and geology and so on. So our responsibility is in the evenings to help them out with viewing the stars. And so it'll basically be, we're going to try to have a lot of telescopes, maybe about 10. And then the kids will be doing hands-on learning how to use very simple telescopes. So I think the main issue with logistics will be getting out there and back, but I'll be in contact with people with more details in the newsletter, and then a little later we'll be actually recruiting people to agree to do it.
And can you repeat what the Star Party is on the 11th, April 11th?
Anderson Farm Park.
Okay.
On
Thanks.
Upper Providence, I think it is, right?
Okay. All right. Rentals. Joe, you have anything to report?
Sorry, no. Other than we're soon to get an 8-inch reflector to, if we can ever arrange this.
Right.
And Harold, I hate to tell you this, but after you called me today, Len called me, and I said, Len, I thought it was just going to be Zoom tonight, but Harold tells me it's going to be live, and Len says, "Oh, I'm going to go." So
I called him off.
Oh, you did?
I did. He sent me an email. I called him off.
Okay. Yeah, he said, I'm going to meet everybody out there. I said, unfortunately, I can't make it tonight, but I kind of thought it was going to be next month, so,
Yeah.
Oh boy. Comedy of errors.
Yes.
But yeah, one of these days we'll do that, and we'll have an 8-inch available as well as the 6-inch.
Yep. I want it out of my shed, so that'll be good. Especially because I just finally got one of those wagons to help carry everything to the Valley Forge, to the airplane field, so I can make fewer trips from my car. So now they're both taking up space in the shed.
Very good.
Nate Prentice has withdrawn, excuse me, due to some new professional challenges. He's got a new position. So we do not have a camping or star party czar. So if somebody has an interest in helping organize something like that, let me know. And the next thing you know, you'll find yourself in charge of the committee pulling those things together. We've had, pre-COVID, we've had quite a number of really lovely star parties up at Cherry Springs, or some of them have been up at Blue Mountain Vista. And it would be great if we could go back to doing that again this summer. So if you have any interest in that, or particularly drawn to astronomy camping, let me know. We'd love to have somebody else help us with that. And I think that's it for reports until we get to Andrew. I'm so glad you didn't go to Radnor, because you and I also talked about you doing the observing report.
Yeah.
So
yes,
hopefully you're ready to roll now.
I am. Yeah. Let me share my screen. One of the last time. All right. So, how do you do this in Google? slideshow. Oh, there we go. Okay. I graduated school, so I no longer have Office. So I'm resorting to Google now. Okay. So my name is Andrew Hitchner. I'm the observing chair for the DVAA for all of you new members. And this is the observing report for March 2022. Before I get into the report, though, I do want to say a little update about the star parties in case you haven't seen. So because of our low number of star parties that we've had for, frankly, the last few years, we're trying something new. We're trying to have what I like to call a backup date. So the main date, the date that we will always be shooting for having the star parties is going to be on a Saturday. And then we have a backup date, which is going to be the Friday before that Saturday. Now I know it's the backup date is before the actual date, but I call it backup because that's like our second choice date. Because of course Saturdays is a little better for all of us to make than a Friday. So this past star party though, which happened last week, was a great example where we had some crappy weather on Saturday, but Friday night the weather was actually pretty good. So I did call for the star party to be that Friday rather than Saturday. Of course, you know, it's a game between getting people to know, you know, what days the star party is, but also waiting long enough to have an accurate weather prediction. So please be patient while I figure out the timing. It sounded like from Jan's report that at least the DVAAers did make a good adjustment in that we had a pretty good turnout for scopes. And it was the March star party, which tends to be a little lighter. So that's the path going forward. I hope to, you know, at the beginning of the week, I'll let people know that there's a star party going on. And then hopefully by that Thursday, I'll say whether or not it's going to be Friday or Saturday. And then if I feel like people need more time, or if people can act, you know, faster or whatnot, I might change that going forward. But just keep calling the hotline and just keep checking the groups.io chats for any star party news. So, and that's again for new folks, or if you're confused, that's specifically our star parties at Valley Forge National Historical Park. I know we do a lot more star parties now that Jan and the outreach team coordinate. I'm only in charge of the ones at Valley Forge, so that's the only ones that I'm talking about here. And feel free to reach out to me if you have any questions about that too. So here's the observing report for March 2022. And I'm actually going to go back, you know, I've been doing this for a number of years now, and we've had a lot of new members come on. And I thought, you know, it's been a while with COVID. We haven't done a lot of like observing clinics, and it's been a while since I touched on the basics. So I'm going to do a few topics on a few months on just like the basics of observing and stuff. And I wanted to go through this week or this month specifically about observing conditions. And I'm not talking about this, although this is usually what we see living in Pennsylvania. I'm talking about more things like this. So this is the clear sky chart. I think some people call it like clear sky clock. For some reason I call it that, I don't know. But so this is specifically for Blue Mountain Vista. And if you're new to observing, you might hear people talk about this and how you should check it out. And, you know, you bring this up and there are some things on here that are pretty obvious, right? You know, we have cloud cover, obviously, wind, humidity, temperature. We know about those, but what about these other things? Transparency, seeing, and darkness. And you might not really know what those things are. So I'm going to touch on those today. Those are kind of the three biggest things that we talk about when we talk about if the night is worth going out to observe, other than cloud cover, obviously. So let me first talk about darkness, because that's pretty easy. So darkness, obviously, is how dark the sky gets. Now, of course, we know not all night skies are created equally. Some places get more dark than others. So obviously darkness increases as the sun sets. And if we go back to this chart, you know, white means that it's sunlight, you know, it's daytime. And then we have this transition period when the sun sets here. And then we have this period of darkness here. And actually this is due to the moon being up. Obviously, while the moon is up as well, it's not going to be as dark as the sky could possibly be. So the sun sets, it gets darker, the moon's still up. it's kind of bright out, but obviously not as bright as daytime. And then the moon sets and it finally gets the total darkness. So as dark as it's going to get. And then the sun comes up again, and then it's daytime again. So that's kind of what this bar down here is showing. Now, the maximum darkness, if you will, depends on the amount of light pollution at a given location. So like I said, not all night sky places are the same. The darkness that you would get in Center City, Philadelphia is a lot different than the darkness that you would get in the middle of like Yellowstone National Park, obviously, right? Okay, can we hear me now?
Yeah, sorry, I think I muted you by accident.
Oh, no worries. Jeremy, if my presentation is that bad, you can just tell me.
Yeah. We can throw the fruit once we get back.
Yeah, once
No, that's why I clicked by accident.
No worries. No worries. I'm impressed that we got this far without that happening. So there are a few ways that we can measure darkness. One is limiting magnitude. And when we say the limiting magnitude is something, we're saying that is the faintest magnitude that we can see with the naked eye. Now you might hear, people describe optical systems. They'll have their own limiting magnitude too, depending on like your size of the telescope, what eyepiece you're using, etc. But we're talking about with the naked eye to generalize a single place's darkness. Another way that we like to say how dark a place is the Bortle scale. So if you look up dark sky map or Bortle sky map, you'll get something like this. And in the crosshairs here is Blue Mountain. And you'll notice that Blue Mountain here is in the yellow. And if we look over here, we can see what's called the Bortle scale. So the Bortle scale shows how dark a place is, how much light pollution there is, 9 being center city. You're not going to see many stars unless like the really, really bright ones. And 1 being that is a natural sky. That will be, there's no light pollution at all. So yellow here is kind of in between 4 and 5 in that transition between orange and green. That's kind of like where I think the threshold is for when we go like to dark sky observing, when we want to look at like dark, deep objects. And there are lots of graphs or graphics, if you will, like this on the internet. I just pulled one, and this is a great way of showing, 9 over here. Again, if you're in Philadelphia, you're in a 9, and sometimes it's even worse than this. You're only seeing the really bright stars of the constellations, really. And then when you get down to 5 or so, well, now you can start to see the Milky Way when you're fully dark adapted. And then 1, you're seeing all kinds of stuff. The constellations will not even be discernible when you're at 2 and 1. Very, very dark. And it's really the threshold here between 4 and 6, when you start to see the Milky Way. That's where I like to shoot for to go dark sky observing.
I have a question.
Yeah.
Isn't it also, besides your location, isn't it also dependent on the altitude that you're pointing?
Yes. Yeah. So of course the sky will not be a uniform brightness across, right? In fact, for instance, when we go to Blue Mountain, right, the Bortle reading or so that you would get would be different if we're looking towards Allentown over here, and would be different if we're looking, up in this direction. So
what angle of elevation represents what's under the crosshairs?
that is I believe that's a zenith reading under the crosshairs here. I could be wrong. It's probably, if you want to know more, you can contact Barry. I don't know if Barry's on or not. He's the Dark Sky Committee for the DVAA, and he knows a lot about how to take accurate night sky readings. A way that you can do it is using an instrument. There are sky quality meters, or so. I think they're called sky quality meters, and you can buy them. And they're just little photodiodes with a little filter on the top that's a diffusion disk that takes all of the light coming in from the entire hemisphere and then creates a kind of average reading or so across the entire one. And that's another way that you can measure the darkness of the site. So,
yeah, I just used when I lived in Maryland, I was out of the city, and I had really good coverage above like 45 degrees. When I started to get lower, that's local tangent plane, not zenith, not North Pole. But by the time I get down to like 30 degrees, there's so much light pollution, especially from DC, that I didn't even bother.
Right.
That's why I asked. You're saying it, this looks like really interesting right here, but what's the size of the cone associated with that?
Right.
You can't tell that from this picture.
Yeah, I mean, obviously, like a general rule of thumb is that the zenith is going to be your best, your darkest area of the sky, generally. A lot of places, like you said, if you're living down in this location around here, then your horizons are going to be pretty light polluted, whereas looking up to zenith, you might be a little better. So that is another thing to consider. If you're looking for an object or so, you might want to pick your sites depending on how high that object is going to get in the sky. If you know that your horizons are very light polluted, then you might need to go to a specific location if you want to observe a low altitude object for that night. So, that's a good question. Thank you. Okay, so that is darkness. So I want to talk about the next two, transparency and seeing, because we talk about these a lot. And if you're new to astronomy, you might not have heard of these, or you might think that they're kind of the same thing, but they have their differences. So transparency is specifically attributed to atmospheric extinction. And extinction is due to, well, how much light hits the atmosphere and how much light is actually getting through the atmosphere to your eye, or through the telescope to your eye. And there are two things that could cause some loss of light. There's absorption and scattering. So absorption is the energy of photons, and then it's converted to some kind of light or some energy that's no longer visible. So these are pretty big molecules in the atmosphere, ozone or so, and if a photon hits these bigger molecules, then the energy will be absorbed, and then the photon is the energy has been converted and the photon is no longer there. So those are obviously not going to get to your eye. And then there's also scattering. And this is where the light is still there, but it's redirected out of your field of view. And this causes objects to be dim and lose contrast. Such as Rayleigh scattering is one of the main kinds. This is scattering of light from particles much smaller than the wavelength. So you can think of aerosols or so when it's hazy up in the sky, and that's where a photon's coming through the atmosphere, hits one of these like smoke particles or so, and then is scattered out of your direction. So again, this is basically just a loss of light due to absorption and scattering. So if we look here, this is Rayleigh scattering, and this graph has the wavelength of light in nanometers. So we have red light over here, right, and we have blue and purple, violet light over here, right. And then we have the percent of light scattered. Now, if you notice, red light is scattered a lot less from Rayleigh scattering than blue light. And this is what creates pink sunsets or red sunsets. Because when the sun is low on the horizon, it's going to go through a lot more atmosphere before it hits your eye. And there's a lot more chance of Rayleigh scattering to occur. So more red light will reach your eye. And this is also a good indication if you get to a site early, and if there is a very pink sunset, then their transparency, at least at the beginning of the night, is probably not going to be too good, because there's going to be a lot of scattering in the atmosphere and a lot of the light is not going to reach your location. So that's a nice rule of thumb when you get there. And now on the flip side, we have seeing. Now seeing is due to the atmosphere moving in between the object and yourself. And this is most frequently caused by quick temperature changes in the atmosphere. And there are three places where this could occur. It could happen really low altitude, almost at ground level, where, at the beginning of the night, as the surface cools, then that hot air from the ground is going to hit the cold air in the atmosphere, and there's going to be a lot of turbulence. This is a reason why when we like to go observing, it's usually better to not be on things like blacktops or parking lots, It's usually better to be in grassy areas because those parking lots hold a lot more heat, right? So there's going to be a lot more turbulence above you if you're in a blacktop. Then there's a kind of mid altitude where you get some low altitude winds in the atmosphere that's moving radiation and moving the atmosphere a lot. And then there's the high altitude, which is like where you get the jet stream that can bring cooler or warmer air depending on in the upper atmosphere. So I have this graph here, or graphic to show you. So if you're at site A here, you're looking at Jupiter. You're looking through a pretty calm atmosphere, right? So you're getting a lot of fine detail on it. If you're at site B, though, on the other side of the mountain, there could be a lot more turbulence, as indicated by these squiggly lines and stuff. And it's basically just going to blur Jupiter. Now, this is the effective scene. Now, if there was different transparencies, then you would get kind of the same amount of detail, but Jupiter would be darker. Whereas this is more of like a motion blur from scene. So there are instances, generally they go hand to hand, right? If you have a lot of turbulence in the upper atmosphere, you could be getting a lot more dust particles or so. So a lot of times as the scene degrades and the transparency is going to degrade too. But you could have instances where the scene is pretty bad, where it's blurry, but the transparency is pretty good in this case because the relative brightness of the two objects are the same. So that's the difference between scene and transparency. I know when I first started, and even now, sometimes I need to double check, like, what do those mean? So I just wanted to touch base on those for you tonight. And without any other questions, that's all I have. Thank you.
Thanks, Andrew. Appreciate that. I know we have a report from Lou. There's been a bunch of stuff going on with astrophotography. So Lou, take it away.
Okay. This week on Wednesday, we had our first astrophotography workshop in like 2 years, and it went really well. We had great participation. Gary and Tom went over how to get started with astrophotography with just equipment you have. I am planning on posting it on our YouTube channel, but I am sorry, I got sidelined. I didn't get a chance before. I'm in the hospital now, but I'll do it sometime in the next couple of days if you guys want to access it. But we'll have it every Wednesday before our regular meeting at 7:30. Next month, Wayne will be presenting for us. Wayne, do you want to give us a little bit of a preview, or am I putting you on the spot?
Oh,
here?
I'll be
Actually,
the following
Joe.
one.
Sorry.
Joe is presenting next month. And
I'm
then-
sorry. No, I'm sorry. Did I say Wayne? I meant Joe. Joe, I apologize. Joe, you're going to kick my butt. Take it away, Joe.
Joe Wayne,
Well, you sound the same.
Well, I think we'll talk a little bit about, Tom and Gary you did such a great job last month. I'm going to maybe talk a little bit about what you guys did and perhaps take it a little further into actually tracking the stars with inexpensive tracking devices, and talk about that a little bit, and maybe some of the options that actually tracking can give you in terms of recording objects that with a kind of a low signal, like deep sky objects, and maybe go into that a little bit and how that can fit into someone's armamentarium, for imaging the night sky. So that's basically it. Maybe talk about some of those topics.
Well, thank you, Joe. And after Joe, then we'll have Wayne, correct?
That's right.
But so next month, though, is going to be member night, and I wanted to announce this to the entire club. Everybody who wants to participate is eligible. So if you have any pictures that you want to show, please email me or the group at astroimagers@dvaa.org, or you can just post it on the forum with a little note. But since we're going to be live, what I'd like to do is get everybody who wants to participate all their stuff together, with, exposure information or anything else you want to say about the picture. And I want to have it all on a USB disk so that when we go to live at Radnor, we can try to do this as smoothly as possible so that 20 of us aren't getting up and, going back and forth to the projector all the time. If you can't make it, it's no big deal because we'll be streaming. So you can do yours if you're going to be home from your computer. The other thing we're planning after, so our workshops are going to be once a month every Wednesday at 7:30 prior to the regular club meeting. And we're doing it this way just so that we can avoid the new moon and not take any dark sky time away from anyone. But eventually, if May, or after, we'd like to have this with weather dependent. So we'll actually go out and do live demonstrations. So keep tuned here and stay in touch. We'll put updates on on the website on the imaging page. If you have any questions, or if you want to be part of the group and participate, just email us. The more help we have, the better off we're going to be.
And Lou, I just want to repeat that email address. It's astroimagers, ASTROIMAGERS @DVAA.org, right?
Yeah. Mm-hmm.
And then I put that in the chat if anybody missed that.
That'll email
Thanks,
all of it. Me, Gary, Joe, everybody that's on the list. And Wayne,
Super.
I'm putting you on that list.
Super.
Okay.
Thank you. And with
That's all I got.
With that, we come to the presentation part of our meeting, and I will throw it to Jeremy. Take it away.
All right, thanks, Harold. So just to reiterate what we heard before, for our next meeting in April, we will be returning to the Radnor Township building over on Ivan Avenue. It's actually been 2 years since we've been there. It was February of 2020 was the last time we were there. So actually this past Tuesday, Lou Berman, Brian Lee, and I made a visit to Radnor. I had some help from a couple other folks. We were able to successfully live stream from the meeting room. So we identified a couple of issues with audio, just getting good audio quality as people are moving around. So we have to go through the audio equipment that we have in the club's possession, and we may be buying some equipment as well in order to be able to do this successfully. That'll include a switcher, so we can use multiple computers and live stream from those. So the plan will be that we'll use the YouTube only. So the Zoom, if we use it, will just be kind of an internal thing just for presenters. So it's just a lot more complicated to keep track of everything. So the live stream that you can access remotely will be through the same YouTube feed that we're using right now. So with that, very happy to introduce this evening's meeting. I was going to talk a little bit about the April meeting, but I think Lou and Joe did a great job introducing that. So tonight, I'm pleased to welcome back John Conrad. He's a familiar face to many of us and has been a friend to the DVAA for quite a while. So John received his degrees in astronautical engineering from the U.S. Air Force Academy and Purdue University. And he worked for many years in unmanned space programs for the Air Force and NASA, a variety of projects in aerospace, defense, energy, IT, and security. So now that he's retired, he gives a number of presentations on astronomy. So you may remember some of the past talks he's given about the Lucy mission to the Trojan asteroids. He's talked about lunar science and the Apollo program. He's talked about global climate change and several other topics as well. So we're very happy tonight to have John back to talk about kind of his baby, which is rocket science. So tonight we're going to have Rocket Science 101, and this is going to be the first of a two-part series. So if you want to catch the second part, tune in to the same place. That'll be March 25th, next Friday, starting at 7:30 p.m. So with that, I will introduce John Conrad. You're muted.
There we go. Let's see if I'm going to share my screen successfully. Got it? Are you seeing that?
Yep,
Yeah,
looks
you're
good. Thanks, John.
Yes.
Okay. get the thumbnails out of the way. Not that I don't love seeing everybody in a little box in front of me. It's hello and thanks, Jeremy, and hello to all of you in your little boxes. And I can't tell you how eager I am for us to have a chance to actually stand in the same room and see each other. And so feels like that may be coming soon. And so I hope you'll invite me back soon. At any rate, this week and next week, as Jeremy said, we're going to cover a topic, an area that is often mentioned. Started back in the 60s and 70s, and we've all said it at times. You know, the sayings are kind of familiar. It doesn't take a rocket scientist to something or other. That's not rocket science. And such things as that, which sort of imply that there's something really hard and really special about rocket science. And I'm not going to expose the fact, or I should say, I'm not going to say that that's not so. I'm just going to give you folks a chance to come to your own conclusions here, because what we're going to do is cover pretty much everything that typically is called rocket science when you're employed or engaged in those kinds of activities. And it turned out that when I put these together, there was enough material that clearly it needed to be done in two parts. So here we go. And let's see how we're working. Usually the first time I click on these things, it doesn't work. So let's try it again. There we go. All right, so tonight, as it says, we're going to be doing the rocket part of things, the getting into space part of rocket science. And I thought that we ought to start right off noting the perhaps most famous early rocket, for the simple reason that nobody had orbited a man-made satellite until this one did. And it's quite a unique configuration. It proved to be very, very useful to the Soviet Union, now the Russians, such that they still have configurations of today's rockets that are pretty obviously evolved versions of this. So in 1957, that was the first successful launch of a satellite. And not to be outdone, but unfortunately to be beaten in time, came the first US successful launch. And we'll talk about both these in a little bit of detail shortly. But tonight's going to be talking about getting things into space. So as I said, rocket science is a broad field, but it has a very simple mission. And there it is, placing a payload where you want it. It's as simple as that. And it turns out that placing is the part that has the propulsion systems and rockets to get things off the ground. And the things that you get off the ground are called payloads. And that's for a reason, because breaking free of Earth's gravity is very expensive in terms of energy and very expensive in terms of money. And so if you don't get a really good payback, why would you do this? And so it's referred to as the payload because it can be very costly and needs to deliver value. It needs to pay you back. And the payloads ride on top of spacecraft. And the final big piece is where you go, orbits. And while I've just pictured some simple orbits around good old Earth, and frankly, that is where by far the largest number of spacecraft have ended up in Earth orbit. There are many other orbits that we can go into around other bodies, or in the case of a few, actually still headed out of the solar system, and from time to time having their orbit perturbed by something they pass close to. So again, everything in all of these areas that people work in is kind of broadly known as rocket science. And there's way too much, so we're just going to cover the spacecraft and orbits next time. All right, so quick overview of how we got here. And I'm certainly not going to take us back to the early fireworks. You're all probably aware that they probably started in China thousands of years ago. But the things where we actually were controlling something using gunpowder started, and as often happens, they started in order to have something for warfare. And so here are some pictures of Chinese fire arrows. And you can see basically a tube of gunpowder with an end that's open. So you have effectively a nozzle for the thrust. And you attach it to this long pole, which allows your bowman to fire these things, or I should say, shoot these fire arrows into the air. And they also are burning. And the shaft, to some degree, would stabilize them. At any rate, they were used against the Mongols, and that's the first recorded use of actual rockets in warfare. A few hundred years later, these things, I'm sure, had been used in the interim, and by this time, there were some non-warfare uses, and people had had fireworks for many years, in fact, over a millennium, and the Germans came up with the idea that they didn't just want to shoot a skyrocket up that would burst, but they wanted to get higher. And so they actually put a rocket on top of the skyrocket. So when it got to altitude, it went off and went even higher. And therefore, we had our first multi-stage rocket in the 16th century. Another historical event, we're told, is a senior administrator in China, again in the 16th century, had a number of his, I don't know if you'd call them staff or slaves or what, prepare a chair with 47 fire arrows mounted around the base of it, pointing down. And he wanted to launch himself, obviously, from this picture. And what happened is a good rendering of what actually took place, apparently. It's recorded that there wasn't much of anything but smoke and flame. So I don't think he survived. Certainly it wasn't the first successful manned flight, but that's when it was tried. So we move forward a few more centuries. We still used rockets for warfare, and we're all very familiar with it when we sing the Star-Spangled Banner and hear about the rocket's red glare that the Brits used against us at Fort McHenry. And so here we have, what, 6-7 centuries, and there really wasn't much advancement at all. And that's because other things in warfare turned out to be more effective, like having metal cannons that were bored out and could fire warheads that would explode with much more effect than a rocket would. Now we move up to the 20th century, modern rocketry. And this is really the story of, I guess, what you would have to say are the most preeminent modern rocket scientists. They're the ones we looked back to as to really launching modern rocketry. And the first one is a gentleman that you may be able to picture from the 20th century and maybe not. It's probably not the one that comes to mind first. This one's a Russian, and here he is in his old age, I think in about the 20s. He was born in 1857. And Konstantin Tsiolkovsky was a sickly youth, and so he never actually had much formal schooling. His parents, he wasn't a peasant, his parents were middle class, and so they got him educated. And so by the time he'd grown up, it was quite clear that he didn't just have intelligence, but he had a very creative mind. He had hundreds and hundreds of writings on many different topics, including human consciousness, beings from other civilizations or beings from other planets, and of course, rocketry, which is why I'm talking about him. And in the area of rocketry, he wrote a very famous paper which got wide distribution and recognition and became the basis for a lot of the developments in Russia. Even though he didn't have formal schooling, he was recognized by the Academy of Sciences, which is a big deal in all of those Eastern European nations, and became an academician in addition to being a school teacher. And this work, exploration of outer space by means of rocket device, has a well-known mathematical rendering of actually how a rocket works. by an extremely rapid expulsion of very hot gas in one direction and the thrust that is due to that. And so you can look in that book or you can look in the Wikipedia website actually and find that rocket equation. He didn't ever experiment. He just came up with lots of ideas, multi-stage rockets, hovercraft, a space elevator. It turns out when the Eiffel Tower was built, that kind of lit a spark in him, and he thought about building one all the way into space. And so a lot of people still consider this. I think there are websites devoted to talking about whether we'll ever build a space elevator, but the idea was actually there as a concept in his writings in the late 19th century. So he gets these nice titles for his work. The second one that I'm going to talk about briefly is probably the one that came to mind first, the American Robert Goddard from the Northeast US. Here he stands with, in a very famous photograph on a farm actually outside of Boston. And here he's holding in one hand the lower frame of a rocket, the first liquid rocket. The part that's mounted there at the top of the structure is actually an engine that burns LOX and gasoline. And when he launched this successfully, the first historically recorded liquid propellant rocket in 1926, it did a few things. It burned as he expected and expelled and created some thrust. It flew some about as high as a house, and it landed a couple 100 feet away in a cabbage patch. And he was at his Aunt Effie's farm, and she probably wasn't too happy about that. But it was kind of the shot heard around the world for liquid fueled rockets. He did a number of other things in the next couple decades, including stabilizing with gyros, compartment on top for instruments, as well as holding a parachute to bring a payload down softly to the ground. All right, and so now we'll talk about the third of the famous true rocket scientists from the early part of the 20th century. This one is a German, and if I ever pictured in my mind's eye what might be a German scientist, that's a picture of it there. At any rate, Hermann Obert was a professor, and he was a professor in kind of the 10s and 20s, and like the others, or actually more like Tsiolkovsky, he was quite a writer, and he was not only good at writing about these concepts for rockets, including some designs that held up, like the one that was the precursor to the V2. But he was one of those very gifted scientists and engineers that have an ability to communicate with the average person. Once in a while, I know in my college classes, you'd run into one of those, and you're always glad to do that because for whatever reason, things became clearer. He wrote very clearly. It was such a bestseller, you can still buy it today. There's a picture of it taken off of the Amazon website for about $150. You can go out and order a copy of this translated into English. He wrote about a number of things regarding rockets into planetary space. And it was such an inspiration to so many lay people that they started to form clubs to talk about it and to consider doing things like this. So not unlike, astronomy clubs, he spawned a lot of those, the first of the rocket clubs, not just in Germany, but in the rest of the world as well. So he had a grad student, and the grad student's name was von Braun, around 1920, I think. And the earliest actual experiments that he did from his concepts now made into designs of a liquid rocket involved this graduate student von Braun in the late 20s, and Obert was very successful at that. Before von Braun died late in his life, he made it very clear that his inspiration, the number one inspiration in his life, had been Hermann Obert. At any rate, Von Braun was a natural leader. I think we're all aware of that. And when the Nazi Party in the 30s knew, as well as governments all around the world knew, that there was something about rocket technology that was showing promise and might actually carry weapons, the Nazi Party enlisted him. However that's done, I don't think it would be something you would refuse, to lead the team. And they put together an incredibly impressive team of scientists and engineers and equipment and manufacturing on the north coast of Germany at Peenemünde. And we've all read about what's happened with that. They basically, after creating the V1, known as the buzz bomb, they created the V2, which was a very useful, practical rocket. They, stage by stage, took care of each of the systems that needed to be successful, including being able to be pointed and carrying a payload and so on. And here's a test launch in 43, and in 44 they started having operational launches, and believe it or not, thousands of these weapons hit various places in Western Europe, especially the UK, in the last year and a half or so of the war, actually just in the last year. So along this time came a realization, I'm sure, among all these scientists and engineers, that they really had stolen a march on their colleagues around the world who hadn't succeeded, and their value was well known to them. And so as it became clear that Germany might lose the war, they were very amenable to the spies that showed up, and many nations got spies in to talk to von Braun and other leaders and set up rendezvous and come up with some escape plans. And it turned out that these these scientists wanted to be recruited. Probably many more of them would have preferred to go into the free world, to the US, than to the USSR, but the USSR had a big plan too. Fortunately, the plan that was put together for us succeeded in getting the leader, von Braun, and his top people, and well over 100 scientists and engineers out. He actually used, maybe the only time he ever used it, his Gestapo rank in the military to get his people through the checkpoints on the way out and escape. And they also arranged for many rail cars full of parts of the V2s and the equipment and test equipment and so on to be put onto ships and brought to the US. The Russians got their share of German scientists too, but probably we got the best of them. And so the next thing that happened was von Braun and his team were set up by the Army in New Mexico in 45, after the war had ended. And the equipment that had come over showed up on hundreds of rail cars of stuff that we got to start off the US program, to pick up where the V2 development had left off. And the V2, hello? Somebody have a question?
Now remember to mute yourself if you're not, while John's doing his presentation. Thank you.
All right, so let me emphasize the importance of the V2. And remember, this started as a glint in the eye of Hermann Obert. It was practically built and used, and it became the basis for our early ballistic missiles, the Redstone, which had a space version you'll see in a minute, the Jupiter C. And actually the Saturn V is just sort of the nth degree development of the V2 design. The Russians also got the German scientists, and so lo and behold, they had a series of developments based on the V2. They at some point branched off into a different configuration that you're aware of. The Russians, though, with their communist Chinese neighbors in the early 50s, worked out a deal where they got something of value, and they gave the Chinese the prints for the V2 and their evolution of the V2 line. So all three of the major nations and their space programs had their beginnings with the German V2 design. Interesting thing happened in UK, and the UK had gotten some of the scientists and were trying to do their own development program after the war. A civilian group known as the British Interplanetary Society took an idea to, I was going to say Her Majesty's government, but it wasn't Her Majesty yet, it was still His Majesty in 46. And they took the idea there that we should take the V2 and put a manned capsule on top of it and do a suborbital flight, which was rejected. And then 15 years later, that's essentially what Alan Shepard and Gus Grissom did in the US. Kind of ironic. All right, so now we have finally the beginning of the space age, which is to say the first time that we put a man-made object in orbit. So it started at the beginning of the 50s. Now the Cold War was already going on, and both sides weren't thinking, I don't believe, much about rockets getting things into space. They were thinking about rockets called missiles getting things ballistically at the other countries. And so while that was going on, which is to say there was plenty of development going on in all the countries, James Van Allen, which is a pretty famous name now, was a professor at the University of Iowa. And he got some of his colleagues together. They were doing atmospheric science, and they came up with some bright ideas, and they decided that these ideas would be attractive not just to their community in the US, but many of them knew international scientists as well. And they proposed to the US government, which carried the idea forward, to have something toward the end of the decade called the International Geophysical Year. And if any of you are anywhere near being contemporaries, you may or may not remember what I remember reading in the Weekly Reader or the Junior Scholastic about the IGY. It didn't mean a whole lot to me at the time, but it wasn't something that had happened before. It wasn't something that was going to happen again. And it was in the planning stages then by governments around the world to put forward projects to prove things related to Earth science in that particular year. So it was going to be a target date, and it was going to drive some development. And lo and behold, and not too surprisingly, came the idea in the US, as it says here, which was publicly announced for, quote, small Earth circling satellites to be launched in that year. Remember, nothing had ever circled the Earth that way. Within a few days, the Soviets publicly announced the identical plan. The Soviets back then never spoke in public. Everything was under wraps, and so it was quite extraordinary that they would throw down the gauntlet, sort of publicly here, but they did. And we wondered how far along they were, or at least the people like me, and I was in junior high, wondered. And we were all surprised not long after that, when in October of '57 came the announcement and the headlines in the paper and the pictures and the frequency that people tuned into and listened to the beeping of the Sputnik as it went around the world with the first artificial satellite. And it didn't do much except essentially, prove that they apparently were ahead of everybody in terms of these kinds of technologies. And given what the Cold War was all about, which was trying to resist communism and get people on the free world team versus the communist team, it was really a concern in the US. And anybody that lived through that, like me, like I said in school, was well aware of changes in science and math in school immediately. It was like STEM before there was STEM back in the late 50s. The whole math curricula and science curricula were significantly changed in those years because we had the feeling that we needed to catch up. So what happened next then, since they had beaten us up to space the first time, the US had a program underway. As we had said, we were going to launch some small Earth circling satellites. You might be surprised, but it was the Navy Research Lab that was given the job of developing the space rocket, known as the Vanguard. And the reason for that is the Air Force was a brand new service and had only shown up in the late 40s, and it would have seemed logical for them to have the developments for space rockets. But the fact is, the Cold War had both the Army with von Braun's team and the Air Force developing ballistic missiles of different kinds that became the Atlas and the Thor. And so the Air Force and Army were tied up. The Navy got the job, even though they didn't have a rocket team at the time. And it turned out that when they tried 2 months later to launch this Vanguard, it blew up for all the world to watch on the launch pad. Another black eye for our reputation. And there were a bunch of reporters that like to give it crazy names like Kaputnik. At any rate, immediately it was decided at the highest levels, Ike and so on, to give the job to von Braun, who'd wanted it anyway. And so he and his team, who developed a ballistic missile that they called the Redstone from the V2, now just turned it into a space launch vehicle quickly by putting a satellite, or I should say an upper stage on top of it with a payload that was built by Jet Propulsion Lab. And JPL had been building for the Army jet engines, which now had been transformed into a rocket engine here for a second stage since about the 20s. And this one was known as the, I'm sorry, I'm getting a different story going here. This one that you see being held here is the JPL upper stage plus payload. And on the left is Pickering, the head of JPL, on the right's von Braun. The guy in the middle there is none other than James Van Allen, because he got to put his experiment on board and go up and find the Van Allen belts for the first time. So the first US launch, as opposed to a beeping, sort of passive satellite like Sputnik, actually had a lot of scientific value. Anyway, the Army had done it. We were very pleased. NASA didn't even exist. Later that year, it came into being, and still today reports directly to the president. And so it could be said that, civilian scientists wanting to do earth science research were now the ones responsible for getting into space. But in fact, it was really the fact that the Cold War was underway with the missiles now becoming space rockets involved. And it was just a continuation of that. And the Cold War in space was now well underway. All right, so now let's stop with the history and just give a very quick overview of what these things that get us into space are. They have a few simple but very important elements. First of all, obviously, they have rocket engines. And the engines have to burn something, and what they burn isn't called the fuel, it's called the propellants. Often you hear it misspoken. In order to, as we'll see in a minute, in order to get into space where there is no oxygen, you need to carry your oxidizer along. So every chemical fueled rocket has to have a combination of an oxidizer and a fuel. There has to be some kind of a system to control the attitude and aim the rocket. And so various kinds of gyroscope packages and trackers are used for that. And that's fine for knowing your orientation and knowing whether or not you're aimed the right way, but you have to be able to do something about it. And that's called thrust vector control. That's pretty self-explanatory. Some way has to be arrived at to take this massive thrust that's pushing you in one direction and be able to change that direction slightly or change the orientation of the vehicle. Roll would change the orientation around the longitudinal axis, and yaw and pitch change it in the other axes. And the several ways to do that are listed here. Initially, they actually put some very high temperature resistant materials like a flat square into the jet or the rocket exhaust, and they would pivot these so that they would actually deflect the exhaust. And these jet vanes were used, I think, for the V2, but I'm not sure. At any rate, that was an early thing that was done to change the aim of the thrust vector. Vernier engines are simply little engines mounted on the sides of the aft end of the rocket so that you can use them in different pointing configurations to roll and pitch and yaw. But ultimately, everything like today is either a gimbaled nozzle or the entire engine is gimbaled so that it actually can pivot about different axes and aim the thrust that way. Every rocket that you want to get some information back from needs a downlink, the telemetry, for housekeeping information, just to tell you what's going on in the rocket, as well as if you have instruments to send down the data. And then uplink is needed increasingly as you want to do a variety of things with your rocket and command it from the ground. The brains on board started off to be very, very simple, and I can attest to that. I worked on the Thor space launch vehicle in the 60s, and our flight controller, it's hard to say, it was about the size of a small round wastebasket. Inside, there wasn't anything like a printed circuit board. There was wiring, there were mechanical relays, timers, and it took care of telling it to shut down the main engine, MECO, and things like that. So the early brains were very much different than the microprocessors that came along, and then the very much better computers that we're used to having on board today. But some kind of brain was needed. And you especially had to have a command capability, because nations that care about the safety of people around the launch areas want to be able to destroy the rocket if it's not going in the right direction. And we'll talk about that in a couple minutes. All right, so a little deeper into propulsion systems. As I said, 2 propellants are needed to be carried on board. It'd be fine to burn something with air if you were staying close to the ground, but you need to carry your oxidizer up with you if you're getting where the air is thin or into space. The thrust is kind of an interesting term. Most people that haven't thought about it much or had a lesson on it think of it, because it's just kind of intuitive, that you push all this hot gas down toward the ground, and it either pushes against the ground to get you off the ground, or if you're up in the air, it's pushing against the air, except that that's not what it's doing. Thrust is simply the statement of the force that carries the rocket forward, that is the reaction in Newton's third law. And by that, I mean, he talked about for every action, there's an equal and opposite reaction. Well, the action that you control is combusting all these propellants and ejecting them at high velocity. And so it's that mass of propellants at velocity downward that gives you a reaction upward called thrust. That's simply what thrust is. It's not pushing against everything. You do it in space where there's nothing to push against, just like you do it on the ground. And so there are 2 ways, and both are commonly used: liquid propellants or solid propellants. Liquid propellants, if you look at a rocket, are what's inside that takes up most of the volume of what you're seeing in the first stage booster. The fuel tank, the oxidizer tank, they have to be very large. They have to get a lot of fluid down through the pumps into the combustion chamber very, very rapidly in order to burn there and be ejected out the rocket nozzle at the base. And so most of the volume is these tanks, and quite a bit of the other stuff in there is plumbing of various kinds, which is a characteristic of liquids that can cause problems sometime, but at any rate, it's necessary to have various kinds of plumbing and valves and so on. The kinds of propellants are interesting to review. What you're aiming for here with chemical propulsion is reliable and storable propellants that can flow easily and also can give you both the oxidizer and the fuel with the energy to be released when it burns. And in the case of V2, it was a kind of alcohol. In the case of many of the well-known rockets, you see them there, Atlas, the Saturn V booster stage, all of the Falcon rockets, the Merlin engines, they use LOX, liquid oxygen, plus RP1, rocket propellant 1, which sounds kind of exotic, except what it is, it's kerosene. So you have your hydrocarbon and you have your oxygen to burn it. And it turns out you can get a little more effective energy release with liquid hydrogen as your fuel. And the upper stages tend to use that. The Saturn upper stages had liquid hydrogen and liquid oxygen. There are some other combinations of chemicals that used to be used more frequently than they are today. People seem to have settled down most of the time to liquid oxygen and some form of hydrocarbon. At any rate, the Titan, which was used for decades as a ballistic missile and as a space launch vehicle, had nitrogen tetroxide and hydrazine. And the one that I worked with there, since I worked with the Gina upper stages a lot, was quite an interesting combination of not just exotic, but dangerous chemicals. UDMH is unsymmetrical dimethyl hydrazine, and IRFNA is even worse sounding, inhibited red fuming nitric acid. And having walked around where the tanks were and where we stored these and pumped them, it was pretty nasty stuff. You didn't want to be around there very often. All right, so the other kind of rockets, solid rockets. Basically what you do, you take the combination of fuel and oxidizer, whatever chemicals you've chosen, in a liquid form, or at least a flowing form, and you mix them together with what are called plasticizers and binders so you can pour it. And you pour it into this cylinder, which is effectively the first stage rocket body, just like that. And so the cross-hatched area with the void down the center is in cross-section this. It's the grain, and the grain is just the name for the combination of two propellants and the other stuff to hold them together that's been poured in there. And it burns once you've ignited it on the surface. And so if you look at that little diagram in the lower right there, you see that if you ignite the combustion chamber, which is that cylindrical void in the center, it'll burn on all sides of that cylinder and it will burn outward. And of course, as it burns outward, its radius increases, which means its area of burning increases, which means the thrust increases. And you get a curve that you don't want to have, which is increasing thrust as it moves outward towards the rocket wall. And so what they've done from the beginning is they cleverly came up with a way to change the geometry of the hole in the middle, and they call it a star for obvious reasons. And it gives you, just like a coastline going in and out, gives you a whole lot of extra feet that you didn't think you'd have for a round lake. The going in and out of the grain here gives you, if you plan it out right, a very even thrust as it burns outward toward the wall. So that's the way a solid rocket burns and how it's built. So to compare the advantages and disadvantages, when you've listened, if you have like I have, to any of the SpaceX launches or even any of the other launches, but the SpaceX are the most common these days, you'll hear them talking in the first 100 seconds or so about max Q, or maximum dynamic pressure. And basically what they do as they go through the atmosphere, accelerating rapidly, is they lower the thrust briefly, they throttle it down in order to reduce the heating on the vehicle until they've gotten through and gotten to a thinner atmosphere and not so much friction. And so in order to do that throttling, you have to have these valves and pumps on board that can change the level of propellant flow. And that's one of the big advantages of liquid propellants. It's also slightly more efficient than solid propellants. The flip side of that is all that complexity with valves and seals and pumps is tricky to get working. In other words, as you test it out prior to launch, you have all kinds of leak tests that have to be done, and inevitably you find some pipe or some seal that needs to be replaced. So it's trickier to get them working, and those are things that can fail. And it's also got its challenges, since you're talking about cryogenic propellants sometimes, and if not that, then exotic liquids. So there are some disadvantages there. Solid rockets, on the other hand, picture says 1,000 words. They're very simple, and they're once you've poured it, it's very stable. They're easy to handle. They're easy to transport here and there and store. You can store them not just for months, but for decades. And so those are the advantages, but obviously you can't change the thrust level. Once you've ignited that star combustion chamber in the center, it just keeps burning until it's either burned out or it's had a hole punched in the side or something. So the disadvantage is a little bit less efficient in terms of the energy, but it can't be throttled or restarted. And the older grains in the early decades used to have a problem where they'd pour the grain and not know, because it's very hard to see exactly the consistency, that they had some voids or cracks. And if you had one of those, they could get to a place where it would burn through rapidly and then actually burn a hole in the side of the rocket sometimes. So the military likes the solids for the reason that their crews can store them easily, get them out when they need them, move them around, and there's much less in the way of logistics support needed. And the liquids have their own advantages, especially with regard to being able to handle the thrust amount and to have a bit more efficiency. So there's two kinds, and they are used for different purposes. An example of where they both used together is the good old shuttle. That shuttle craft sitting strapped on top of the orange, basically gas tank. That's what that giant orange thing is. It's really just two great big inner tanks, one fuel, one oxidizer. When it's used up, the shuttle flies off of it, or it drops away, falls into the ocean, and was then recaptured and reused. That was a reusable part of that system. And in order to get the extra liftoff thrust, they had two very large solid rocket motors that burned up in the first couple of minutes and then were dropped so that you can have the lighter weight while you're just flying with the liquid engines after that. So that was the shuttle's approach with a hybrid of liquids and solids. The Saturn V is always worth kind of looking at and thinking about. Sort of the, like I said, the nth degree liquid rocket so far. The first stage, the Saturn I stage, was effectively a 300-foot tall building filled with 5 million pounds of propellants that all burned out in the first 168 seconds. And then the rest of the rocket on top of that would, of course, separate and move on the upper couple stages. And so it was just a wonderful use of liquid propellants. All right, so I said I'd come back to this briefly. A very important part of US launches has always been having on board a command destruct capability. What it is, as far as the specific item and what it does, it's a shaped charge. And the shaped charge was talked about in the days of IEDs some 10 years or so ago. Effectively, it's high explosive that has been formed in a way and is ignited in a way so that it doesn't just blow in all directions, it blows in a particular direction very rapidly. And so you put these shaped charges at a strategic point, typically above the propellant tanks or near the engine, so that when the command comes to destroy and the shaped charge fires, it stops the it stops the thrust right now. I mean, that's the whole goal. Is accidents can happen in that these rockets can go in the wrong direction in a hurry, or they can start to break apart. And either way, you want to destroy the pieces before you have the thrust carrying the pieces anywhere. And that's what the command destruct is for. And a very important individual shows up on the launch team controlling the range. He controls the ships at sea because in the case of the US, at least, all of our launch sites launch over water. He controls the traffic out there to make sure that ships are out of the way. He watches for any traffic, including trains in the area. And in general, what he's trying to do, first of all, is protect humans from any danger that happens if the rocket goes the wrong way, and also protect valuable property. He does it with a button, literally, that he has. And so he watches and he knows when it's off track. He can see the orientation. On board also, just so you understand and are more comfortable with this perhaps, there are also accelerometers that are sensing whether or not the thing's starting to go out of bounds in terms of roll or pitch. And so it'll self-destruct. It's questioned many times of whether or not he hits the button before the vehicle tells itself to explode. One interesting feature, though, is you want to watch the vehicle. It's why we keep the human in the loop, because if it is going awry, but it's headed over water, you want it to get a ways out there before you explode it. You don't want the pieces to come down on land. And so you look forward to having this kind of debris field on the water as opposed to on land. And so you want to have him have the capability to wait and destroy it later if he wishes. An interesting feature where I worked at Vandenberg was that the range safety officer and the people who were running the launch kept in touch as the launch window was approaching an opening, because there were railroad tracks that had been there long before Vandenberg Air Force Base was built along the coast west of Santa Barbara. And there was a decision made, for better or worse, in about 1960, not to pay a huge amount of money to reroute the railroad tracks around the reservation. And so for the 10 years, or for the years I was there, and I guess ever since, they've had to work around train schedules. The range safety officer keeps track of the schedule, so he knows when things are supposed to come. But of course, trains don't always run on time, so you have to have a physical capability to find where they are approaching from south or north, to predict arrival time, to predict time it goes through. A lot of our conversations in the last hour or so were often about whether the train was going to be there before the launch window opened, that sort of thing. There were many launches, I was involved in a few, where you delayed things for trains, and there were a number of them where the launch window opened and closed, and because of a train, you didn't get to launch that day. And since it costs many tens of $1,000s an hour to run a range during a launch, it was a very expensive proposition. And one that they may have regretted they didn't move the tracks in the first place. All right, so who has this capability to get into space? You know, the first couple. There was a first race, which was to have a man-made satellite in orbit. And the folks that run that, we've talked about. Today's organization is called Roscosmos, and they've been in the news as their director has cast aspersions on anybody that doesn't agree with Putin's war in the last few weeks. You may have read that in the paper. At any rate, that's their agency. And there we are, coming in a close second. The next country that had their own capability was France. The French, have always had good technology, and they have a lot of pride. So they pushed hard and had their own rocket by the mid-60s. There was a mini space race that took place in Asia, where the Japanese and Chinese tried to beat each other. And that particular space race we thought was going to be won in 1969. China had a launch, but it failed. And the Japanese, a few months later in 1970, succeeded and beat them. So that was the way that little race went. The Brits, you may or may not know, had their own rocket launch capability because they didn't want to be outdone by the others. And it was viewed as important to their national security. But they and the French and the Germans all got together and formed something in 1979 and had their first launch as a total space agency, the ESA, the European Space Agency, and have, essentially surrendered their single nation status to the group to have their launch site, which is quite well known. We'll see it in a second on a map in South America that they use for their launches. And the Indians, who always have good technology, had their first successful launch in '80. So that's 7 individual nations at that point. There are 10 total. Here are the other 3. Israel had a space launch starting in '88. Iran, 2009, and the North Koreans, we're all aware, have succeeded in doing that as well in 2017 and since. So other nations could certainly have their own capability, but it became unnecessary and financially not the right approach. They would rather, pay one of our nations to launch their spacecraft, and in some cases their astronauts. The Canadians certainly could have had their own launch capability if they wished, but instead they've invested a lot in becoming a very important satellite builder through the years. And you probably heard about this when it took place a couple of years ago. It was sort of the year of the Mars launches. And one of them, lo and behold, was by the United Arab Emirates, UAE. A lot of people surprised at that. Their Hope spacecraft is currently in Mars orbit, so it was very successful. But understand, this didn't give them space launch capability because what they had was money, and they used it to basically build their spacecraft with US universities. I think Colorado University led the team that built their spacecraft, and the Japanese was the capability that they used for launching it from Japan. So they don't actually get up there as a spacefaring nation in the sense of having the ability to get into space. The budgets are kind of interesting to see. Now, these are the published budgets from a few years ago, and the pie chart kind of says it all. There's the US, there's the Europeans, and there's the 7 little dwarfs, I like to say. And here we've got a grand total of published budgets of about $41 billion, which you can probably guess, for starters, that's the NASA budget. It's not the Department of Defense space budget. And certainly the Chinese are not going to tell you what their budget is, nor have the Russians. And so the story really has to have the military included, and it also has to acknowledge the fact that there are commercial customers, so that the nation's budgets themselves aren't involved in commercial customers like Inmarsat launching communication satellites. So the whole story is hundreds of billions of dollars a year being spent on these. And I have to say, in the last certainly 10 years, for whatever set of reasons, and Elon Musk might have a fair amount to do with it, the pace of space launches has picked up every year. All right, so where do they launch from and how is that determined? The key word in the title is major. There are literally scores, maybe hundreds of launch sites around the world. If you count in sounding rocket launch sites like the US and Poker Flat in Alaska or out in Barking Sands in Hawaii. I've launched from both those sites, but not into orbit. But the major ones are all pretty well known, limited to the major spacefaring nations. And to start with, and there are 13 of them around the world, they're all north of the equator, and that's because effectively the developed world and most of the landmass of the world is north of the equator. And so some of them are next to the water. And I mentioned before the concern of safety when you launch these giant burning missiles that might explode or come down in pieces. So we'll take a look here quickly. The US launch sites you're very familiar with, two on the East Coast. Now that we've added wallops, has become very commonly used in recent years. All on the water, as I said. Why do we have one on the West Coast too? Well, the answer is there's a need to launch to take advantage of the Earth's rotation, and the Earth rotates from left to right, from west to east. And so you literally, as you lift off, get to take advantage of the velocity of that point on the Earth's surface as you move in an easterly direction. So it boosts your payload capability to launch to the east. And the closer you get to the equator, the better, because as you can imagine, an object at the equator goes a lot further around. It goes 25,000 miles around in 24 hours, and that's a much faster speed than if you're at north 45 degrees and you're going many few thousands of miles less than that. So the closer you get to the equator, the more push you get. We have the consideration of putting, the Cape down there as our farthest south point. If you want to go into an orbit that doesn't go generally east-west, but is inclined around the poles, a polar orbit, which is very useful if you're looking down, because the Earth rotates underneath and you go around and you see all of the Earth over and over again. You have to be able to launch for safety where your rocket can go north or south and fly over water for a long time. And there isn't any place on the East Coast where you can do that. And so lo and behold, if you look at the West Coast line there, the coastline, you may know that there's a point where it makes a sharp right. And that point is just west of Santa Barbara. And that's right where Vandenberg was put, so that you can comfortably launch to the west, to the southwest, and especially directly south, and go over water for a very long period of time and have safe launches into polar orbits. All right, so I mentioned before, the Europeans put their launch site down on a piece of land that they own, French Guiana, in Kourou. And it was used not just by ESA and by the US, for example, in the James Webb Space Telescope launch in December, but it's been used by the Russians, who paid a lot for it for years. And the Russians just departed a couple of weeks ago after the war was begun. And who knows when they'll return. They've sort of pulled their chips off the table, left people hanging. It's quite a terrible situation right now. The Russians themselves, now we'll go to the Eastern Hemisphere, have these 3 launch sites that are their major ones today. The 2 on the left have been used since the beginning. The upper one is in the European part of Russia. The one right under the ellipse there with the Russian name is actually in Kazakhstan, and that's where their manned launches including all the astronauts that we've launched in about the 10-year period when we didn't have our own launch capability, went from. And the one out there in the east still isn't on the water. And that's opened, I think, in 2017. So it's going to be used increasingly. That's their most modern one, I guess. The Chinese, for their part, if you ignore the one at the bottom there, the one that's on the water, the other three are the ones that they've used for all the years of their space program. And the one at the bottom is pretty new. And as you see then, the 3 Chinese sites and the 3 Russian sites don't seem to care as much about dropping pieces of stuff on people as we do and as the Europeans have, which is an interesting comment. Hainan Island is that little island off China in the south there, and that's where they put their launch site recently. So they're getting a little more safe, and they also have a better capability for polar launches from there. The Japanese have a site called Tanegashima on Southern Island, and the Indians have this also on the water launch site on the eastern side of their nation. So that's it for the major sites. Oh, I wanted to note here that you may have caught that I said nothing is launched in the US except from those. You've been watching, perhaps like I have, the SpaceX Starship, which is quite an impressive and giant booster that Musk and his company have been trying to get FAA permission to launch into orbit. And they haven't got the permission yet, so they've kind of hedged the bet. So they may or may not get permission to use this Boca Chica launch site, which is right at the very southern tip of Texas before you cross into Mexico. And if they don't get permission there, even though they'll probably continue development, they have a backup on the Cape where they can launch the Starship from there. All right, so we've been talking about chemical propulsion, and since the beginning, this type of propulsion has, by every measure, been what has been important for getting into space. And yet there are other types of propulsion, and they're worth mentioning. Ion propulsion, you've probably heard of, essentially accelerating electric ions in an electric field. And you can almost understand just how efficient on the one hand and not very practical on the other hand that is. We've been developing these ion engines with names like Hall effect for decades now, and a number of them have been used, but never used to actually fight gravity and get off the ground. They don't have nearly enough thrust for that. The thrust I call paperweight because it's essentially like what it feels. The force is like a piece of paper sitting on the back of your hand. That's kind of the thrust force. But if you've got time and you are you aren't fighting gravity, then you can build up and accelerate to a useful velocity, as we did with the Dawn spacecraft, to get from one large asteroid to another over a very long period of time, about 10 years ago. Another new type of propulsion, and this one isn't practical, but it is interesting to think about. It's a project that we'll show you the name of in a second, but essentially Stephen Hawking, in the last 10 years, and of course he's passed away now, but he and his team came up with a concept and quite a bit of the paper design for what are called nano spacecraft, extremely tiny spacecraft that will be pushed by photons of light, and whether it comes from the sun or it comes from a laser. And so with enough of these, they came up with a design that says you can eventually accelerate a useful spacecraft that you've placed out in space and just shined at essentially for a long time until it accelerates to a very high velocity, 20% of light speed. And so breakthrough star shot, as they called it, would get to Alpha Centauri, the nearest star, what is it, 4 light years away, in about 20 years. And then you could send a message back at the speed of light. And so it would take another 4 years for the message to come back. And it would be nice because you'd know that you'd gotten to the nearest star, which is at this point kind of unimaginable. But at any rate, you would be going so fast when you went by there that it wouldn't do you much good, but it would be interesting to accomplish. Another type of propulsion is a warp drive. We've all heard about those. And of course, you're aware it's really not a thing. But even as I say that, a lot of heavy duty intellectual talent has applied their thinking to this. And one particular gentleman in the 90s, Alcubierre, I guess is how you say that, and you can go on Wikipedia and read about this if you want to, has designed something called this Alcubierre drive, which people have taken shots at and been skeptical of, but nobody's been able to shoot it down yet. It isn't really a propulsion, though. It does get you up to very, very high speeds, much further than 20% light speed, but it does it not by propelling you, it does it by folding time-space in front of your spacecraft. So enough about warp drive. Another one you're probably going to be hearing more about in the near future is nuclear propulsion. And like I said with ion propulsion, this isn't new. It was well known as far as designs and possibilities back in the 50s and 60s. At the Nevada test site, they actually, the Atomic Energy Commission was the sponsor of a couple programs. The first was Rover, the second was NERVA, where they built operating nuclear propulsion rocket engines. And that's simply by effectively having a reactor sized with a working fluid that gets heated up and then forced out a nozzle, like, you know, every other kind of that kind of propulsion system, using nuclear energy in that way. To use nuclear energy in the more dangerous way, which is to say with a fission device, a bomb, there's a concept that you might enjoy going out and looking at the video of online. If you just look up Orion, the nickname for it is the putt-putt, because effectively what it is a very large space vehicle with the people at one far end and with what's called a pusher plate behind pistons at the other end, and they basically push fission devices out and explode them behind the pusher plate, and the pusher plate transfers the energy from that giant explosion to accelerate the spacecraft or the entire vehicle, and it moves along quite nicely, accelerates very fast. It's much more efficient than chemical propulsion. If we could develop either one of these capabilities, they're more efficient, and there is talk of needing these to, let's say, in a more practical, time-wise way, getting back and forth to Mars, for example. So it may very well be in the news before long. All right, I've come to a point, and I'll ask Jeremy. I've got about another 10 minutes or so here on some of the rocket capabilities of the billionaire companies now. I can talk about it now, I can do it next time, or we can just skip it if you want to just go to questions.
What do you guys think?
Snoring.
I had a question.
Okay, why don't we just go to questions? Shall we do that?
Yeah, on that last chart, the one you just about the fuels, the ion engine, the Hall thrusters, the Hall effect thruster, that obviously can't be used to get you off the ground.
Right.
But once you get into low orbit, you can use it to take it to upper orbit. And in fact, some of our geosatellites, in fact, do that.
The
They
geosync,
go
yeah.
from an injection orbit to the geo orbit using the thrust, the Hall effect thrusters.
You're exactly right. Yep.
Takes a little. Actually, the first time it happened was an accident. The main engine, upper stage engine didn't work, and so fortunately the designers had cross-strapped them, the fuel tanks, to the Hall thrusters. So they switched their injection strategy, or their final orbit trajectory insertion, to using the Hall thrusters. And what should have taken them a few days took them, a month or something. But they got there. And because the nice thing about the Hall or any ion engine is that it's, in terms of fuel efficiency, for those who know about fuels, I'm talking about specific impulse. Their specific impulse is, anywhere from 10 to 100 times what the chemical engines have. So a little fuel gets you a long way if you have the patience.
Yeah, they regularly use them for station keeping of the geostationary spacecraft.
Sure.
We do have a
Any
couple
other
of votes
questions?
to hear about the billionaires.
What's that?
So we do have a couple of votes to hear about the billionaires.
Well, I can take about 10 minutes and do it if you want me to.
Yeah, you want to do it?
Sure, why not?
Yes, very
Go
much
for
so.
it.
All
Why
right.
not? It's early.
This is the space race for the rich and famous.
That's it. Okay, here we go. So this isn't the future. This is stuff that's been done. And there's been quite a lot of extraordinary changes, actually. Musk and SpaceX win the prize for, I guess what I'd have to say is best intrusive technology in a very, very long time. Reuse by vertical landing of not just the booster, but other things too, is such an extraordinary game changer to the cost equation that we've seen what's happened there. And he's got big dreams, and so hopefully his company can stay solvent and keep moving us forward, not just to the moon, but beyond. And I think there's a lot of hope for that. Anyway, he was so successful after setting up the company in 2002 and having, if you've ever read any of the books, about 10 years of plenty of failures, just like most new companies and new technologies have. So most people know him in the last 6-7 years, maybe. The 10 years before that wasn't pretty, just like most startups aren't. But they were relentless and they solved the problems as they came and ended up giving us a capability that I have to say I never imagined we'd have. Here is their core successful vehicle, the Falcon 9, because it's got 9 Merlin engines. Here it is, not lifting off, but landing on a barge at sea. There it is after the launch legs come down in like the last 1 second before it actually sits down, sitting nice and stable on one of those automated ships. And here it is, the Falcon 9 with 2 more strapped on the side for a grand total of 27 engines at liftoff. And here comes my favorite ever. And I remember watching this in real time when they did it. And those 2 on the side that were separated early came down simultaneously, vertically landing adjacent to each other perfectly. It was, I don't know, this kind of thing that we used to see when we were kids in space movies, and I didn't think I'd ever see it, but there it is. And now they've done it like 100 times, I think. The other big recent success is they designed and built the Crew Dragon with some pretty new and useful features that have all worked very well and gotten us back with a manned capability. Better than the companies that have been around for decades trying to do it, as I think we're all well aware now. Hopefully, because we're no longer going to necessarily have access to the Russian backup launch capability, although we do have an astronaut up on the ISS right now who's just broken the record for most days in space in one mission, who's coming back, I think, at the end of the week or maybe next week on the Russian, with the Russian capability. So whether he'll be the last one to use their capability for a long time, I don't know, but we do need to have a second player. And so hopefully Boeing this time around, as opposed to when they tried 2 years ago and last year and didn't succeed, will be able to demonstrate their capability. The next billionaire actually started his company 2 years earlier in the year 2000, named his suborbital vehicle the New Shepard after Alan Shepard, the first US astronaut who didn't go into orbit but went a suborbital flight. And so lo and behold, here's his vehicle lifting off with its capsule on top there. And here it comes back down to land vertically with the capsule landing elsewhere and kicking up dust, and the legs come out. And just like Musk and his company did, Bezos has now succeeded in reliably having another vertical landing reusable booster. It's great. Now, the next thing, I guess I have to just tell you, I'm a little bit cranky about the term astronauts. I get very annoyed. I have classmates that flew the shuttle. I know a lot of people and what they go through to become astronauts, let alone once they've been named, at the years they wait and the training and the work that it is, and to call these people that are just basically passengers on a really great amusement park ride, not to be too cynical about it. I mean, that's nice that they get to do it, but they are not astronauts. Here's a picture of the Blue Origin, I think the first capsule that landed. And in this case, Bezos has this configuration inside for them to see outside very comfortably and float out of their couches and so on. And they've had, I think, 3 flights now. None of them yet have been full paying passenger carrying. And here's one of the crews, and I just love to see Captain Kirk finally getting a chance to go into space there. All right. Next, I like to talk about the air-breathing entrepreneurs, which is not to say that they don't have gills. It's to say that a staged vehicle doesn't need to start with a rocket booster. It can start with an aircraft. And so you use the aircraft to get altitude and some velocity, but mostly altitude, such that the rocket then that is launched from the aircraft can get you up into space. And that's what each of these folks are doing in various ways. Paul Allen, yet another billionaire that you may know was the co-founder of Microsoft with Gates, had his own set of billions. And so he invested in a really solid set of test pilots and their development company called Scaled Composites in the 90s. And by this joint venture by 2004 had come up with this configuration, a couple fuselages under a center fuselage, and hanging underneath it, and that's called the White Knight carrier aircraft, and hanging underneath it, Spaceship One, now separated before the rocket lights up and it goes up into space. And that's the configuration that, per the rules of the competition known as the Ansari Prize, had to demonstrate, I think in a 1-month period, 2 piloted flights successfully getting above the defined altitude for space. And they got there first. This combination, they won the prize. I think it was a $10 million award. And Paul Allen turned around immediately. And the next billionaire, Richard Branson, bought the technology from them. And what Branson then did in forming the company called Virgin Atlantic was to update the configuration of both the carrier aircraft, now called, of course, the White Knight II, and the rocket vehicle, now called Spaceship Two. And here it is hanging, and there's no center fuselage as there was before. And so this takes it up to altitude. They had a number of tests in the about 5, 6, 7 years ago. And finally, in 2018, they had the first powered flight with the test pilots flying it to get up into suborbital space. Then they had some passengers on board for a test flight, and then it was deemed as safe for real passengers. And so here we have the one of the great PR pictures of all time, Richard Branson weightlessly promoting his cabin in the first flight that we all paid attention to, I imagine last July, I think it was. And sitting in the seats around him there, and now down on the ground, here's another PR picture. Here's a man promoting a very expensive ticket for a fun ride into space with 3 of his employees. But it was quite a great accomplishment. And we have entered the age with Branson and Bezos of passenger carrying at least suborbital flights for the time being. And of course, there have been some really wealthy folks that have paid for crews to go up on a Crew Dragon now too. And Musk has used his capabilities and his company to support those. So more air breathers. Paul Allen had another approach after he sold the first set of technologies to Branson. He started a company called Stratolaunch. And you may have seen this extraordinarily, and I think world record holding large double fuselage 6-engine aircraft, which unfortunately, after being rolled out and then having some taxiing tests before flying, Paul Allen passed away in 2018, and we sort of all wondered what'll happen to this capability since it hadn't flown yet. And another investor called Cerberus kicked in, and they have now not just flown it, but they've flown it in 4 flights. The highest altitude is 40,000 feet. So it's getting ready to launch something off of that wing mounting there. And this is just an artist concept of a few different concepts they have for hypersonic vehicles and space vehicles that might be launched by the Stratolaunch. We'll see about that. At any rate, that's another air breather. And last but not least is another round with Richard Branson, who's invested more of his money into an orbital capability, not just the suborbital with Virgin Galactic, but Virgin Orbit now uses one of Branson's Virgin Atlantic 747s, which has been modified and named the Cosmic Girl. And here it is with a rocket hanging underneath the left wing in there, close to the fuselage. That's launcher 1. And they've not just had drop tests, but they've ignited the rocket. They had a failure or 2, I think, and now they've had at least a couple successes getting small satellites into orbit. And the customers are kind of lining up from NASA and commercial customers. So that's the highest, most visible view of what the billionaires have been doing with rockets. And if you read up on any of this stuff, there are probably a dozen other rocket companies now, a couple of which have had some successful launches, much smaller. I'm trying to remember the names. There are just too many to list, but it's a burgeoning field that'll shake out within 10 years or so, and we'll find out if companies like Branson's Virgin Orbit and a few of the others that have small satellite launch capability all survive, or if just a couple of them make it. All right, folks. I think of you guys now as Delaware Valley amateur rocket scientists, and I appreciate your attention. And any more questions?
I have a question.
Sure.
So thank you very much for that presentation. That was wonderful. I like very much your historical perspective on the whole issue. And I would like you to use that historical perspective to look at the future. So if you were to compare, for instance, the early sea voyagers, sailors that, dared to go through across the oceans, and the progress we've made from then to, launching rockets. When you look at our ability to really go to the wide universe, to reach the nearest stars and others, where are we right now with our technology? Are we still close to the early sailors, or have we gone beyond, do you think?
I mean, that's the big question, and my opinion is no more valuable than anybody else's. I may have thought about it a little bit more than others, but I think that there are a couple things that could become game changers. One of them has probably been mostly accomplished by the step taken by Musk to get reusability, not just in the first stage booster, but in the others as well. In other words, to change the cost equation in a very significant way. I mean, it was a step change. It wasn't what we'd been trying to do since 1950, basically, which was whether it was using solids with more efficient specific impulse or you trying other fuels. None of the chemical rockets working that way ever really showed anything but a small gain in terms of pounds to various orbits. And yet now that's changed significantly because of the reuse capability. So that's one step that's been taken. And it'll be interesting to see, because most nations now are quietly or noisily trying to say that within a few years, this company or that investment or that lab is going to have their capability to do vertical landing, reuse kind of things. But another thing is, when are we going to step into, and it could be simply with the moon, the return where the actual dollar value of the returned minerals or whatever resources exceeds the cost to get there and get them. There are wonderful science fiction shows like The Expanse, if you've ever wanted to think about that for asteroids, with the Belters, who are, many generations of humans out there living in the asteroid belt, mining things so that Earth can have that value back here. I mean, that is, I think, a very realistic thing that somewhere in our future is getting the value of resources in space back to Earth when the cost equation works. It's not going to happen soon, but the soonest time we'll figure out if we might have some chance of it is by looking around more at the moon. I mean, these bases that they're talking about putting at the moon are certainly going to be looking for valuable resources that could be brought back. I'm rambling, obviously. As far as, colonizing the solar system is going to be limited to Mars and the belt, probably. And I should add some moons. So that's probably realistically in the future. A long way in the future, probably. Beyond that, interstellar travel isn't something that is even able to be thought about until we come up with suspended animation, seriously, that actually can be proven to work so that people can actually live through the generations it'll take to travel the distances and then be awakened in time to, be awakened to be out there. The things that are in science fiction movies now. But that's just, fiction. As far as finding an Earth 2.0, we're going to be probably increasingly reading, especially when Webb starts looking at exoplanets around star systems within our galaxy, certainly not in other galaxies, that have all of the latest thoughts about what it is to be habitable. We'll be thinking about that. We'll start counting how many systems there are and how many, and then we'll find some that have the best chance of being almost precisely like Earth before long, I would bet, maybe in the next 10 years or so. But finding them and being able to bridge that space is just, that part, there's no way to imagine doing that. Now, I'm not the kind of cosmologist or mathematician that can read the stuff about this warp drive idea and know whether or not that or wormholes or anything like it has any possibility of actually working theoretically, let alone practically. I did work on the energy program when the Department of Energy was being formed to know that the great investment we were making in thermonuclear fusion was the one that was just going to pay off, and that was in the 70s. And here we are, 50 years later, and it's still at least 20 or 30 years away. These are things that, and that one isn't just theory. I mean, that's something, someday we're probably going to do that. But the things that have to do with bridging the expanse of interstellar space, there isn't anything that really has even been conceived yet that could be put to an engineering test. So the thing we don't talk about, the dirty little secret, you will, of going to Mars is already known to the astronauts in Earth orbit and known to pilots that fly at 40,000 feet or above. There is life-threatening mutations. There are life-threatening mutations that take place even in our atmosphere, let alone long periods of time in outside the atmosphere from cosmic rays. And we'll have to come up with ways to address that as we think about the things that people like Elon Musk talk about very glibly about moving thousands or tens of thousands of people to Mars. There are some real human health problems here that I'm not sure that they aren't an obstacle that we won't be able to figure out for a while.
Thank you.
Yeah, really good question. Fun to talk about.
Do we have other questions?
Yeah, question. This scheme for sending microsatellites to Alpha Centauri by accelerating them using a laser beam and a solar sail, what is the power density of the laser beam going to be?
That's not a field I understand enough. There was an article, I didn't actually show the last part of that slide. I meant to, because there may be some Penn State grads here and I thought they'd want to see it. Penn State just had an announcement in the last couple weeks. Let me see if I can go back to that slide.
Oh, you have to reshare.
I'll do that in just a second. Let me find.
But while he's looking for that, Henry, Avi Loeb wrote a book called Extraterrestrial, where he talks about the entire screen sail, that whole mission to Alpha Centauri. And I think he talks about the laser beams and the sizes of the sails and so forth in that book.
So the article I read a couple of weeks ago is that Penn State's been working on Hawking's concept for a few years now. And they've got something they call Starship Light Sail, which isn't nanospacecraft. It's actually a great big sail. And they're, of course, working on the thinking about not just the materials, but how they would create the large sail such that it could dissipate the heat from the many, many high-powered lasers that would be shining into it, effectively like a big billowing sailboat, filling it up with photons. That's the idea. That's where the research has taken them at the moment, and they've published it out there. I thought you'd be interested to know that Penn State folks are hard at it there. It's a different concept, and they're trying to figure out something that might actually work.
Sorry, what was the other book somebody was recommending?
It's Extraterrestrial by Avi Loeb. I'll put it in the chat.
Thanks. Because if the laser beams are powerful enough that you've got trouble dissipating the heat, even assuming that mostly it's reflected off an almost perfect mirror to get the double thrust, I'm sort of wondering what happens if it hits a satellite on its way up.
You're wondering what happens to the satellite?
If the laser beam on its way up hits some satellite that happens to get in the way.
Yeah, good question.
And how soon somebody starts deliberately picking off the other side's satellites. It does seem to me this, if you've got enough thrust to be worthwhile, this could too easily be weaponized.
I am sure that you're correct, Henry. The few slides I dropped out, one of them was talking about why we're going into space, and it kind of ended up talking about the military reasons. And so you're all aware that there was a lot of splash over a new military service known as the Space Force, which stood up, I'm going to say, I think it was 4 years ago, maybe 3. And you've noticed that I can get cynical about certain things. When I graduated from the Air Force Academy and went into the Air Force, and the space program was just beginning, with classmates and many other grads that have now flown space vehicles, we're all very happy that we were the Space Force for decades before we gave it a name. Having said that, I've become convinced, I guess, that China in particular is enough of a threat in space that we do need to focus more simply on that instead of the Air Force, which was kind of splitting its focus between what's in the atmosphere and what's above it. So now we're just, and you may or may not know that the Space Force is like the Marines, in that the Marines are part of the Navy. The Space Force is actually part of the Air Force. It's another branch, and it was called Space Command just before it became the Space Force. And it's been there for years, but now they can focus on the kind of risks that Henry just brought up, because just like there are people that do mischief with laser pointers to pilots sometime, I mean, there are crazy people doing things like that, and there are crazy nations or ill-meaning nations that will use lasers as weapons in space, I'm sure.
I heard an interview with Jonna Levin this morning. I was listening to it, and she said that the physicist John Wheeler, when he gets contacted by crackpots, he puts them in touch with other crackpots who contact him. And apparently they come back to him and go, "Why did you put me in touch with this guy? He was crazy." They apparently crackpots do not really see that they're nuts in the mirror, but it does seem to me like an amusing way of dealing with that situation.
Yeah. If only it would be self-correcting.
Mm-hmm.
John, I have a question. First of all, thank you for a very good talk. When I was growing up, actually going through high school in the early 70s, I worked on cars. And someone asked me, what's the thing that was most fascinating me about working on cars? I said, it's not making them go, it's making them stop. So around the same time, of course, I followed the Mercury, Gemini, Apollo missions, and of course the space shuttle. And one thing that also always interested me, and of course I'm not an engineer, is once the engines are fired on the launch pad, what the hell keeps them on the ground until they're released into fly up into space?
There are various ways that's done. The rockets I launched didn't have anything holding them down. In other words, they were freestanding and just lifted off. But you do see, I forget what they're called. Anyway, you do see configurations that where there are hold down bolts until it achieves a certain level of thrust, something like that, a hold down bolt, and they break free at that point. Even as I say that, I'm not sure I know what I'm talking about there.
Yeah, I've heard of that also, John. It just fascinates me that something can be built to hold something that powerful down for that length of time.
Well, I mean, think about it. The engines for the Space Launch System, this giant Boeing vehicle that is being rolled out for the first time right now. I imagine you've read about it. The engines in the Green Run, it was called, were tested in Louisiana on a launch stand there at full throttle for 15 minutes or something. I mean, you can hold things down and then undo them and move them away if you engineer the hold down properly.
Thank you.
The Russian
I think the tricky
launches
part
are-
is,
what's that?
I was going to say the tricky part is to design the shear bolt so that it breaks at the thrust you want it to. For example, on the shuttle, the main engines, the ones that are fed by the hydrogen and oxygen out of that big ugly tank in the middle, that has about 3/4 of a million pounds of thrust. And that, since it's liquid, you can turn it off if they decide not to launch. And that's, the shear bolts have to hold that in. But then when they fire the solids, which you can shut off, then you're committed to a launch. Those, as I recall, were 1.5 million pounds each thrust.
Something like that. Yeah, they were in the million class.
So you need to design something that for sure is going to hold 3/4 of a million pounds, but for sure is going to break at 3. I think that's a trick. I know my snowblower has shear bolts on it.
Yeah, mine break often, actually.
Yeah, when it hits ice, they break.
Yes, they do.
And that's a good thing, because otherwise I'd have to buy new blades.
Mm-hmm.
Fortunately, I have spares. I don't know of other technologies other than something akin to a shear bolt that holds the rocket on the platform. But I know it's important to get enough thrust before you attempt launch, or else you'll have stability issues.
Mm-hmm.
Well, it's getting late. Do we have one last question for John before we'll all get to come back? And I sort of feel like Ed McMahon on Johnny Carson show. You've told us everything there is to know about rockets, and wrong. We're going to do another episode and get the rest that we haven't gotten. Do we have a last question for John? And John, that was a great program. Really.
Actually, I do.
Go ahead.
I was wondering if you had an update on the BE4 engines that Blue Origin is developing for the Vulcan and for their own use and for the SpaceX.
No, I don't, but I fully understand your question. I track it every time it happens to show up in the news. One thing I know is you've got one very upset CEO of United Launch Systems, who's been waiting now for years for something that was promised earlier. And Bezos' company has not yet succeeded in getting there. The last I read was a vague kind of a statement that they believe they'll have it delivered by the end of the year, something like that. But I haven't seen a news item on it in months.
Yeah, thank you.
It has not delivered what it was contracted to do to that very big, eager, anticipating launch company, and they need it.
Yeah, especially now.
Yep. Yeah, especially now with the situation with the Russians.
Yeah. Thank you
I
very
mean,
much.
we really do need Boeing to get a launch or a manned capability going so that we've got a couple of them.
Yeah. Thank you.
Folks, I really enjoyed it, and I look forward to talking to you again next week about spacecraft and orbits.
Thanks, John. And I'm glad to know that you probably won't hurt yourself leaving the Zoom meeting like you did a couple of years ago. So I'm really glad to know that. But we'll catch you next Friday. Thank you very much.
Great. See you then.
One other thing I want to mention before we stop the recording is I want to thank Lou and Missy Varvarizas. They put together a basket for a STEM festival a couple of weeks ago for, I think it was an auction. I'm not sure, but it was great PR for DVAA and it was much appreciated. That's the kind of outreach we like to do. Helps build the brand, as it were. So with that in mind, where's Jeremy? Did he disappear?
No, I'm here. Just got my
Okay,
camera.
Jeremy, you can stop the recording and we can move to the virtual party, as it were.